Welcome to homework.
So let's draw the pulley. The pulley here and then we have a mass here. This would represent mass sub 1. This would represent mass sub 2, and we can draw the free body diagrams for both of these. Going straight up would be force tension, and this would be going straight down rather, would be m sub 2g, and then going straight up would again be force tension, and going straight down, m sub 1g. So at this point, we can assume that this pulley is small enough that part of the cable that is touching the surface of the pulley is negligible. We're going to ignore any force on the cable due to the pulley itself. We're going to say that the density of these cables are uniform, and we're going to then treat the two cables as two masses on each side of the pulley. That's what this diagram represents here. And then we can say that the mass sub 1 would be equal to y times m over L, and mass sub 2 would be equal to L minus y divided by L times m. So essentially, we can take the downward motion of m sub 1 to be the positive direction of m sub 1, and then we're going to say upwards for m sub 2 is positive. So force net on the first chord would be equal to m sub 1g minus force tension. This would be equal to m sub 1a. We know force net sub 2. This would be equal to force tension minus m sub 2g. And so this is going to be equal to m sub 2a. Therefore, a is simply going to be equal to m sub 1 minus m sub 2 divided by the sum of the masses times a factor of g. Let's solve for a with using the masses that we find here. A would then be equal to y times m over L minus y divided by L times m, all divided by ym over L plus L minus y divided by L times m. Keep that factor of g. This is going to be equal to y minus L minus y divided by y plus L minus y times that factor of g. Acceleration would then equal 2 times y minus L divided by L times g. And then we're going to divide by L. So this would be 2y over L minus 1, again, times the coefficient of g, rather. So this would be equal to the acceleration, and this would be your formula for the acceleration for part A. Now, for part B, we can say that if we want to find the formula for a final velocity, we can say that A will be equal to 2y divided by L minus 1g. This is going to be equal, by the definition of acceleration, dv divided by dt, or change in velocity with respect to time. And this would be equal to the change in velocity with respect to the position on y times the change in y with respect to time. So that's just simple algebraic manipulation. This would be equal to v times dv over dy. And so we can say that 2y over L minus 1 times g dy would be equal to v dv. and then we can integrate. So we'll integrate from y naught to L, and then here we'll integrate from 0 to v final. Therefore, g times y squared over L minus y to the L, evaluated, my apologies, evaluated at y naught, or y initial, times L. This would be equal to v squared over 2 evaluated at 0 and at v final. And so we can solve and say that g times y initial times 1 minus y initial over the total length L would be equal to v final squared over 2. And then we can solve for v final equaling the square root of 2gy initial times 1 minus y initial over L. This would be our final answer for the formula for the final velocity. This would be our answer for part B. Now for C, if y initial equals 2/3 times L, we can just simply solve. So v final would then be equal to the square root of 2g times 2/3 times L times 1 minus 2/3 L divided by L. And so this is simply going to be equal to 2/3 times the square root of the acceleration due to gravity times the total length L. This would be our answer for part C. That is the end of the solution. Thank you for watching.